Assalamualaikum warahmatullahi wabarakatuh. So today I'm going to present our group assignment for the subject Theory of Machines. This is our final project for the semester, and the topic that we choose for this project is the automated door mechanism, where we are required to design a door mechanism that can close and open automatically using only a single motor. So here is the list of our team members. So the task that we are given to do is, as I said earlier, we are required to design a mechanism that could open and close a door using only a single motor. So in this presentation, we are going to explain about how the mechanism works, the dimensions of the mechanism, the position, velocity, and acceleration profile of the mechanism with respect to the input and output link, and we will also explain why we choose this specific type of mechanism and dimensions. As you can see, this is the door mechanism that we designed using SolidWorks. It is a 4-bar mechanism. Here is the input link. This is the output link, which is also the door. This is the connector link, and this is the ground link, which is the door chassis, or you can consider it as the wall itself. So the motor that was supposed to be included in this mechanism is placed inside this box. As you might notice by now, this mechanism look like the conventional door dampener like we used to see in the office door. It is quite the same, but the concept behind it is totally different. This is the detailed dimensions of our mechanism. This is the door just now, the door link. This is the ground link, which is also the wall link. This is the input link, the one that drives by the motor, and this is the connector link. As you can see, this is the part list. The shortest link is the output link, the door link, and the longest link is the connector link, which connect between the input and the output link. And the second shortest link is the input link, and the second longest link is the ground link, or the wall itself. From the previous mechanism that we saw, what we can analyze from it is that this door mechanism is a non-Grashof mechanism. The reason being is that it does not follow the Grashof equation, which states that the shortest link plus the longest link must be less or equal to the other links. So this mechanism that we design does not follow the Grashof rule. So by that, the motion of input and output links are restricted until a certain degree. The degree here, the restriction degree, is determined by how much we want the door to open. In this case, it is 180 degree for fully open and 0 degree for fully closed. And the motion of the input links that being driven by the motor is restricted by that. Okay, now let's move on to the analysis of the mechanism. So as you can see here, this is the position analysis between the green line, which is the input link, and the red line, which represent the output link. Now, the graph here starts when the door is fully open, and it ends when door is fully closed. So if you want to read it the other way, just read it from right to left instead from left to right. So let's say we want to read it from closed to fully open. So the degree of both input and output link will be almost the same, which is, as you can see, at 180 degrees, fully close the door, and the input link will almost touch the wall. So as they move on to open, they will start to deviate further and further away. and at this point you can see a fluctuation occurs at the output link. The reason being is at this exact point the door begins to open more than 180 degrees, means it opening behind the wall. This can be a case if we have a door that is placed at the corner of a wall where restrictions of the wall doesn't happen. So okay, now let us move on to the velocity analysis. The properties of the graph representing the velocity analysis is the same as the position graph, where when t equal to 0 is when the door is fully open, meaning it open, we can enter through it, and when t equal to 1 is when the door is fully closed. For a better understanding, I think it's better we explain it from closed state to open state. So first thing to note here is that when the door is fully closed and fully open, the velocity of both input and output are the same, which at zero velocity. What this means is that our system is fully functional, where the output and the input motion should stop when the door is either in fully open state or fully closed state. The next thing to note here is that the motion of the input link is amplified by the output link. What this means is that less input motion required to produce a large output motion. And the last thing to note here is that our input and output velocity plot, if you can notice, is almost similar to the harmonic motion graph. This way, we can ensure that there is no sudden spike in velocity, no sudden acceleration or deceleration in the door movement while they are closing or opening. This way, the door can be safe for people to use, as they can predict the door movement. Okay, now moving on to the acceleration analysis. The properties of this acceleration profile is the same as the velocity and position analysis, where when t equal to 0 is when the door is fully open, and when t equal to 1 is when the door fully closed. So this is a graph that represents the closing motion of the door mechanism. What we can see here is that when the door starting to close, there's an acceleration. The door will become faster until it reaches almost 90 degrees with respect to the wall or the ground link, and then it's starting to decelerate back until it reaches zero acceleration when the door is fully closed. So it's quite easy to understand, but how about the opening motion of this door mechanism? So unlike the previous velocity graph, where we can just slide between right to left or left to right in order to analyze the different velocity profile of opening and closing motion, the acceleration profile for the opening and closing motion needed to be inverted with respect to the y-axis. It means that this graph of closing motion need to be mirrored through y-axis. Then we can get the opening motion of this door mechanism. It's basically the same, where the door will start to accelerate first and then decelerate when it is fully open. Okay, now let us review the mechanics behind this automated door mechanism. The main reason why we use the specific type of 4-bar mechanism, which is a non-Grashof 4-bar mechanism, and the exact dimension for it, is because firstly we wanted the door and the input link to be as flat as possible with respect to the wall. What this means is that we want the mechanism that we design to have smallest footprint possible, so it doesn't interfere with other things on the way. Second reason is we want a moderate torque on the output link, so it is safe for people to use and stop the door when they needed to do so. This is proved by the velocity and acceleration analysis in the previous graphs before. And if you can call back, there is just a slight amplification of the input link to the output link, which means that the power generated or the torque generated on the output link is not so much difference with the input link. Only slight amplification happened there. And the third reason is we want no spike in acceleration and velocity of the output. So it is user friendly and would not hurt anyone. So I think we can understand that easily. And the last one is we wanted to achieve our objective of just using one motor, which is located in the small box at the input link for controlling the motion of this door, the opening and closing motion. Okay, before you close the video, go check the link in the description where we shows the animation of the door mechanism that we designed. That's all from us. Thank you. Good luck for your final.